To start, let's recall the Navier-Stokes equations. For an incompressible fluid, we're going to limit ourselves to an incompressible fluid in this discussion. And so we have two equations. We have the equation that represents the continuity equation for a constant density fluid, and we have the equation of conservation of momentum, which is du dt plus, well, this is a vector equation, du dt, u dot the del operator equals minus 1 over rho gradient of pressure, and the viscous term with the Laplacian of velocity square. Okay, so equation 1, of course, is represents mass conservation. For constant density, and it appears as a kind of constraint, like a kinematic constraint to the general time-dependent equation of motion, which is the momentum equation. The equation of motion 2. So we have a little bit of a problem here. So one note, second note, and we have a little bit of a problem here, which is the following, that there is no, if I write the way I've written these equations here, there is no obvious way to couple the velocity and the pressure. You see, this is a particular problem of the case of incompressible fluids, in which our conservation of mass reduces to this equation. Of course, in the case of compressible fluids, we wouldn't have this problem, because we would have the relationship between density and pressure provided by the equation of state, and we don't have this here. You see? So in case of compressible flows, we have the equation of state, which provides a relation between density and pressure. We don't have this in this case. So what do? Okay, so then we're going to have to do a little bit of a work around for this problem. So we're going to write this out so that you'll understand what we're doing all in 2D to make it easier, because we're going to write component-wise the equations. And so component-wise, we have conservation of mass is written out here. And the two equations for conservation of momentum, we have the unsteady term. This is the first equation for momentum, so the equation for the first component of velocity, u. So we would have u du dx plus v du dy. And we have on the right-hand side the pressure gradient in the x direction, and the viscous term Laplacian of u. And our second equation for v, oops, that's a v then. You have to be careful here, not make a mistake. V minus 1 over rho dp dy plus the viscous term now with the Laplacian of v. Okay, so we're going to take the divergence of the momentum equation basically by taking the derivative of the first equation with respect to x and the derivative of the second equation with respect to y, and then adding up. That's our divergence, worked out now term by term. And so let's go slowly here. I'm going to take the derivative of this first term with respect to x and swap around my two partials because I'm assuming continuity, so I can do that. And so I'm going to write d dt of du dx. Then I have a couple of products here that I'm going to take derivatives, so let's go one by one. So du dx times du dx plus u, and take the second derivative of u with respect to x. So I've taken the derivative of this product here. Now I'm going to get the other product, the second one here. So dv dx times du dy plus v, second derivative of u with respect to x and y. And on the right hand side we are assuming constant density, so we keep that guy untouched, and we take the second derivative of p with respect to x. And since I'm running out of space, I'm just going to write here, and then we're going to work with this term later, so I'm just going to write here d dx of the Laplacian. So I'm going to write the Laplacian in the short way like that for you. And then I can fit my other equation underneath here, d dt of dv dy. And again, I have a couple of products here too. So we have du dy dv dx plus u, and second derivative of v with respect to y. So I've got the first product, good. Now I've got, take derivative of this.
Shouldn't that be dx dy and not dy squared? It's taking the dy of dv dx, the second term.
So I'm taking derivative of this term, and so it's du dy, and leave this untouched. And then u, and we have yx, that's correct. Thank you very much. Y and x. Y and x. Thank you very much. Good. We have now, we're taking the second term, right? So we have dv dy and dv dy, so that term appears squared, plus v, and the second derivative now we have of v with respect to y. Now that is the term correctly there. And the second derivative of p with respect to y, again I'm going to write the Laplacian term in its short way here so that I can fit all my equations. So now I'm going to add them up. Okay, so let me add up. So these terms I'm going to add up. This one and then this one. I'm just going to do it in this order. 1, 2, 3, 4, 5, 6, 7, 8, like that. Okay. So I'm going to write them. Let's look at the left-hand side only. Okay, so the left-hand side terms are, we have d dt of du dx plus dv dy, and these two terms plus I have du dx squared. Let me maybe write it, it's shorter that way since I don't have that much space, plus du dy dv dx, bear with me here, we got those two, let me scratch them out so I don't make a mistake, and I'm going for these two now. U second derivative of u with respect to x plus u second derivative of v and x, yx, that doesn't matter, but let's write it that way. And so I've got these two now, plus dv dx du dy, that's this one, plus dv dy squared, that's this one, v second derivative of u with respect to x and y, this one, and finally v second derivative of v with respect to y squared. So I'm going to take now these four, yes, the ones with u and v, I've already worked this out, so let me, these four, and notice the following, that here we have, I can combine the ones with u, and I also have a du dx, ddx, so I will write u ddx of du dx, and that's the first one, plus dv dy, and that's going to be the second term up there. Follow me, everyone? Okay, and this one plus v dy of du dx plus dv dy. Right? Okay, so, well, it happens that here we have the divergence of velocity, so this is 0, this is 0, the same here, this is 0. So we're only left with 1, 2, 3. Well, these two can be put together, so I'm only left with du dx squared plus 2 du dy dv dx plus dv dy squared. You agree these are the only terms left in the left-hand side? So we'll use that one again. That's our left-hand side. Let's look at the right-hand side now. For the right-hand side, we had minus 1 over rho, and we add up those terms, and so we have the Laplacian of pressure, adding those two terms there on the right, plus and now I'm going to write out the whole term that involves the Laplacian. I wrote in shorthand in the previous workings, and so I'm going to write, we had ddx of the Laplacian of u, so that's second derivative of u with respect to x plus second derivative of u with respect to y. And then I also had the partial with respect to y of the Laplacian of v. Okay, so let's look at this guy and write it out. Third partial of u with respect to x plus third of u x and 2 y's plus third partial of v and y and 2 x's plus finally third of v with respect to y. Okay, so now I'm going to combine this one with this one and this one with this one, and I'm going to have partial, second partial with respect to x, you see I have here, and this one is going to be du dx, and this one's going to be dv dy. Plus, and again here I can take out the partial, the second partial, this is a 3, the second partial with respect to y, and I have again du dx and dv dy. Right? So this again is 0, this again is 0 because of continuity. Okay, so now we can finally write the whole equation out that we obtained, which is our left-hand side. I'm going to actually swap the sides. I'm going to write the, where all of this is 0, so I'm only left with this, right? So minus 1 over rho, and I have the Laplacian of pressure. Equal to what we did in the previous slide, which was, it had basically, if I remember correctly, I can't find it on my notes, I had 2. These ones I need to remember what they were. Du dy and dv dx, right?
Yes.
And finally we had the dv dy squared. So this is an equation of the following type, which is a Poisson equation. We have a Poisson equation for the pressure which ensures that continuity is satisfied. And gives us a relationship between pressure and velocity that we can use now to couple our two equations for the Navier-Stokes, to do a Navier-Stokes computation. We're almost ready to go on to steps 9 onwards, but before I want to do this a little bit differently. Everybody happy there? So far so good? So you understand the pressure satisfies a Poisson equation with this function on the right hand side. In the continuous problem, now we want to use this in a discretized approach, and we use it a little bit different in a discretized approach, as follows. Well, forget about that. We already got the final result. So now what I'm going to do is something a little bit different, but we're going to look at the Navier-Stokes equation in vector notation. Now we know we're satisfied, we're happy that we can do it term by term. But I want you to look at the equation in vector form. And now we're going to think that we're going to need a discrete approximation to this equation. And we notice that we don't have a direct way to couple the pressure with the velocity so that continuity is satisfied. We derived a Poisson equation for pressure, but for the numerical solution, we're going to do the following. We're going to first discretize in time. Let's just use, for simplicity, although it's not generally recommended, you understand already that first order methods can produce substantial numerical diffusion and errors which might be excessive, but for simplicity in our discussion, let's just use a first order forward Euler in time, so we can actually write the time derivative as un plus 1 minus u divided by delta t, as we've done 100 times, and so I'm going to And we want an explicit method, so I'm going to immediately multiply by the delta t and take un to the other side so that I can write u n plus 1. This is actually a vector. We just want to write less, and so write the vector, equals un plus delta t times this whole thing on the right. Well, I'm going to have to move this term to the right as well, so there's a minus sign. And these all are evaluated at time n. So, like we did before, we take the divergence of the momentum equation. When I did it just before, I actually wrote out the two equations in 2D and took, my derivatives with respect to x of the x component, derivative with respect to y of the y component, and added them together. What I'm doing is just applying the divergence to the whole momentum equation, and here I'm going to do it in vector form without writing out all the components. Okay, so I'm going to take the divergence. I can leave this guy outside because it's just a number. And here we have minus divergence of this whole thing inside here, n dot and this one becomes the Laplacian of the pressure, and then we have this. We can swap around the differential operators, and I'm going to write the Laplacian outside and then that one in there, n. Okay. Now, we would like to solve the Poisson equation for the pressure like we did before, and you see that what we did before was all in the continuum world. And in the continuum world, we know that we can apply our continuity equation, and every time that the divergence of velocity appears, we make it equal to 0, and it cancels out. Now we're in the discrete world. In the discrete world, maybe while we're advancing step by step in a numerical calculation, it could be that in the numerical scheme, we want a divergence-free velocity at the next step, right? But we may have that at the previous time step, because of errors in the numerics, is different than 0. So we don't cancel out these terms now because we don't know that they're 0 in the discrete world, okay? So we're going to move to the, we're going to do our Poisson equation now in the discrete world and isolate this pressure term and put all the other things on the other side. I think I wanted this pressure to be n plus 1. Sorry about that. We want the pressure. And this is really going, this numerical approach that we're deriving here is actually called a fractional step approach, because what we're going to do is we're going to solve these two equations, the momentum equation and the Poisson equation for pressure, alternating within a time step. So we solve the momentum equation numerically. The divergence of that numerical velocity might not be 0. Then we solve the Poisson equation. We force the divergence to be 0, and basically we correct the velocity with that Poisson equation. Then we solve Navier-Stokes, then we solve Poisson, and so on. But it's like, basically when you're solving Navier-Stokes, it's like you're just advancing half a step in time, really, and then you're correcting with the pressure to obtain u at n plus 1 which satisfies both Navier-Stokes and conservation of mass to a good approximation. So we want now to move to solve a Poisson equation for P at time n+1, which is the following. I'm going to multiply over by rho. Let me just write this out because I worked on this very hard and I'm still finding mistakes. I found a mistake again this morning that probably will creep up later on, and I ask for your patience until we sort all of them out, because so I've divided over by delta T to get my pressure term. Okay, that's good. And this term has a minus, and I've also multiplied by rho to isolate, of course, this term is the one that we want to isolate on the right hand side now. Take that to the right, so multiply by rho. Okay, let's see if you agree. And I have this term, is the one I'm writing out. And we have rho times nu, which is actually mu, right? The viscosity, the dynamic viscosity of the fluid. So let's write it out that way for the time being. Okay. So basically, the velocity field that we are producing with the Navier-Stokes equation is not completely divergence-free in the numerical approach. And so you can think of this velocity, I was think of the velocity obtained from the Navier-Stokes as an intermediate step so it's a un plus 1/2, and the divergence of this is not exactly 0. So we need to calculate the pressure P n plus 1 that satisfies, so that continuity is satisfied. And basically we put this un plus 1/2 in here. So this is a way to interpret it, yes? This one? Yeah. This is 0. We want this to be 0. And we force it to be 0 by making this equal to the rest. Which is exactly what I'm saying here. We solve for P n plus 1 so that continuity is satisfied. Everybody agree with that? So, this is why we do steps number 9 and steps number 10.